Hello everyone, this is going to be a quick discussion about how we use the bisection method to solve an equation like this. If I've got some nasty thing like y equals the cosine of x minus x multiplied by e to the x, and let's just say I want to solve this when y equals 0, then I am going to have, well, an impossible time to try and solve this analytically. There's no algebraic solution to this. There's no way to rearrange this and isolate x like you would expect. So the only choice we really have is to try a numerical solution. So I'm going to, first of all, have a quick look at the function. So there I've typed it onto my calculator and I have a look. And here it is. There seems to be more than one 0, but I'm interested in the positive one. I'm interested in this one over here. I know I could just press the buttons on the calculator to find out, but I'm trying to teach you the process by which this might have been done numerically in the past. So the idea of a bisection method is that we choose x values, two x values, one where the function's positive, the other one where the function is negative. So we call these x lower and x upper. So L and U for upper and lower. And as you can see here on the calculator, if I choose a value, these are decimal too. If I choose x equals 0.2 for the lower, so 22.4.6, and 0.8 for the upper, then the other thing I want to do is calculate the function of xl and the function value of xu. So I can either type the 0.2 into the formula here, which would be a bit tedious I suppose, or I could do a y calculation here, and if I put 0.2, we see that the y value is positive like we wanted, 0.7. I might just mark that spot there. So 0.73, that's all I really need to know, that it's positive. 0.74. I wanted to know the function value when we were at x equals 0.8, the upper. So I'll do that again with a y calculation, x of 0.8. The function here is negative. I'll also mark a red spot there. So that negative 1.08. Now I'm not so concerned about what the value of these functions is. The actual numbers here doesn't matter so much. What's important is that they're opposite in sign. One's positive, one's negative. Now that means clearly I've got, there we go. Clearly I've got 2 points here on the function on either side of the 0, the solution that I'm looking for. Now as an approximation, I'm just going to guess that the midpoint, in other words, the bisection of these, is going to be closer than either of those to the 0 of the function. So this plus this would be, well, here we go, 0.2 plus 0.8 divided by 2. That's going to give me a midpoint of 0.5. And you guessed it, I'm going to calculate the function value at the midpoint to see whether it is positive or negative. Again, I could type it into the calculator, but here I go, 0.5. And I've got a very small but positive value. The function there, positive 0.05. Now I'll iterate this. That's my, if you like, my 0th iteration, or my initial guesses. So this will be the number of iterations. If I go to my first, so there we go, that's the first attempt. My next iteration, I will choose different lower and uppers. Now which lower and upper? I certainly wouldn't want to use these. They're both positive. That's bad. I'll use these two. Now not these two values, these two x's. So I'll put 0.5 and 0.8 as my lower and upper boundary this time. I already know the value of the function at x of 0. It's positive 0.05. I already know the value of the function here. It's negative 1.08. What I really need to do is find the midpoint here. So the midpoint is 0.5 plus 0.8 over 2. That's 1.3 So we have 0.65. Now I need to evaluate the function at x equals 0.65. The function is negative 0.45. Negative 0.45. That's my first iteration. Here's my second iteration. I do not want to use these as my lower and upper boundary. The signs are the same. I want these as my lower and upper boundary. Well, I want the x values that correspond to these. This is my lower x, 0.5. This is my upper boundary now, 0.65. I already know the function values. It was positive 0.05 and at 0.65 it was negative 0.45 just from here. So I have opposite signs for my lower and upper boundary. I find the midpoint again and I continue. I can do this as many times as I like, and once I get lots and lots of iterations done, I'll find that these numbers here, they don't start to differ. They might agree, they might have the same to the first 3 decimal places, and any discrepancies are beyond 3 decimal places. If I was happy with accuracy to that level, I could stop at that point. Now, that's the gist of the bisection method. You can implement this in Excel, and it's not too difficult to do, as I'm sure you could imagine, if you understand how to use formulas to calculate results. You would enter these as your initial guesses, and the rest of this could all be done with formulas. Over here you'd need a few decisions to decide which of these two were similar sign and which were opposite signs, but that's not too bad. I'll leave that to you to have a look at another day. That's enough for now to give a basic idea of what's going on.